Hi there, and welcome to Inside Quantum, the podcast telling the human stories behind the latest developments in quantum technologies. I'm Dr. Stephen Thompson, and as usual, I'll be your host for this episode. In previous episodes, we've talked about various aspects of quantum computing and quantum information with a focus on the theoretical side of things. But how can these ideas be applied in the real world? Today, we'll talk about some of the cutting-edge experimental setups being used to investigate quantum physics and to design the next generation of quantum technologies. It's a great pleasure to be joined today by Dr. Tiffany Harte, a Senior Research Associate in the Many-Body Quantum Dynamics Group at the Department of Physics, King's College, University of Cambridge, who doesn't just work with experimental quantum physics, but also works with some of the coldest objects in the universe. Tiffany, thank you for joining us.
Thank you so much for having me.
Before we get to the quantum systems which are colder than deep space and why they're so interesting, let's first talk a bit about your journey to this point. And let's start at the beginning. What first got you interested in quantum physics?
So I think physics in general for me really came from reading fantasy books when I was a child and a young teenager. So my main motivator to become a physicist actually came from reading Philip Pullman's His Dark Materials. And I just found all of the science that was embedded into those books so exciting. So you had all of the kind of touches of particle physics, the quantum physics that was coming in, the parallel universes. And so I started reading up about some of the science behind this. And the more I read, the more exciting it seemed. So decided that studying physics at university was absolutely what I wanted to do. Certainly at that stage, I didn't have a preference about types of physics. I enjoyed everything, to be honest. And it was fantastic during my undergraduate, having such amazing lecturers who all made their topics sound so exciting and really brought everything to life. So what really got me interested in quantum was actually my first summer project. So this was as an undergraduate at the University of St Andrews, and I did a summer project in the ultra-cold atom group led by Dr. Donatella Casatari, and I loved everything about the lab. It felt like magic. It felt like I was inside a fantasy book already, and just everything I read about the goals of the experiments, everything I learned about how you implemented the experiments, just all seemed just so exciting. So I really just followed that through, kept working on projects that I thought seemed the most exciting to me at the time and that I enjoyed the techniques for, and that led me down the path to quantum.
So you always wanted to be an experimental physicist then, basically from the first time you set foot in a lab, you knew that's what you wanted to do?
Yes. I think I really can trace it back to the very first lab tour when I was first being interviewed for that summer project. It just felt like coming home.
And would you say that's the point when you decided that you really wanted a career in this, or is that the point where you thought this is interesting, it's worth pursuing a little bit further, and then the career just kind of snowballed and came later?
That's a good question, actually. I'm actually not sure about that. I think at the time, I think it was enough that I wanted to spend more time there. I wanted to spend my summer working in that lab, and that project really got me interested in doing a PhD in the field. I think from the beginning of my undergrad, I'd been interested in doing a PhD and going into science research without much idea of exactly what I wanted to work on. So I think it probably did snowball in a sense. So I just kept following the projects that I enjoyed, and I'm still here. So
Well, that sounds like a very rewarding way to do it, right? To work on things that you enjoy and to have that turn into a career.
Exactly. Yes. Yeah, I think probably maybe in the last couple of years, I've had to think a bit more strategically about kind of finding a career path. There's probably maybe a more established track between undergraduate, PhD, even onto a first postdoc that is fairly well worn in a sense. And I think it's probably after that different career trajectories start to diverge so much, and you really have to start thinking about how you want to kind of carve your niche, where you want to find and establish your own research expertise. So yeah, I've had to do a little bit more strategic planning in more recent years, but certainly I wouldn't want to work on anything that I didn't find exciting.
I guess that's the career stage where it starts to get very competitive, isn't it? And I think one of our previous guests said that in research, you're almost building yourself as a researcher and building your own profile as a researcher as much as you are producing research. And I guess this is the point at the kind of the stage where you've been a postdoc for a few years. That's the point where that really, really becomes true and really becomes important for whatever next steps you take.
Yeah, that's an interesting way of putting it. I think that's quite true. You've got to really balance building up your research, which is why we're all here. It's what we're all interested in doing. But you're absolutely right. Yes, establishing yourself as an expert and really working out where you can be most effective as well is, I think, maybe, part of the job that I hadn't anticipated. Gosh, sorry, I'm just having a crisis brought on by by that. No, that's certainly not part of the job that I'd anticipated when I first saw all of the exciting lab work that was going on.
So then, if you hadn't gone down this route, I mean, it sounds like this was a calling as much as it was a job to you. But if you hadn't gone down this route, what else do you think you might have done instead of becoming a physics researcher?
There are so many exciting things. I think very early on, I knew that I wanted to be some kind of scientist. So I feel that I always would have found some route into some kind of science research. It's certainly what I feel happiest doing. But I do think the more you read into different kinds of science, the more interesting everything seems. So yeah, certainly some kind of scientist, but there are so many options. I wouldn't want to say which.
Fair enough. Well, then let's get back to what it is that you actually do. And can you give us a summary of what your research involves? What's the big picture goal of the field and where your work fits into that?
Absolutely. So I'm an experimental cold atom physicist. So we cool atoms down until they're a few hundred nanokelvin. Our goal for our newest experiment is to get even lower, down into picokelvin, so just billionths of a degree above absolute zero. And once atoms get this cold, all of their quantum properties really start to emerge. So you can build, for instance, one of my experiments is in quantum simulation. So the idea here is that we're building a very highly controllable, fully quantum mechanical model of other systems. So in our case, trying to simulate the behavior of materials with certain geometric structures. And because you're working with atoms, building up this experimental model of a system that in reality is made up of electrons moving around in a potential created by ions, the atomic system is much bigger, it moves much slower, it's much easier to measure, and it's very controllable. And on top of that, you've got all of these quantum properties that are emerging because you've got the atoms so cold. So you can really use this as a platform for simulating the behavior of complicated quantum materials. So that's one aspect of the cold atom field, and it's increasingly branching out into lots of different application areas. The other experiment that I am building currently is using atoms for quite a different purpose. So still cooling them down. We want them to be extremely cold, extremely easy to control. When I say easy, relatively easy to control. And we want to perform atom interferometry. So the idea being that we split a cloud of atoms, let the two halves, or create a superposition of states, two states separate in space and travel different paths, and then recombine those atom clouds and read out the interference between them. And that interference pattern will tell us about how those two different arms of the interferometer have evolved. So if they've experienced anything differently in the way that those atom clouds will evolve in time. And so we can use this to make extremely precise measurements of anything that will change the evolution of the atom cloud. So whether that's tiny external forces or anything that's coupling into the atom to change, say, its transition frequency. So the atom interferometry is used for lots of different applications on Earth. So it's used, for instance, for very precise measurements of locally of gravity. But my experiment is part of a bigger collaboration called the Aeon Collaboration, which is a consortium of 7 UK institutions, and we're aiming to build an atom interferometer that can be used as a detector for dark matter and gravitational waves. So using that very, very precise kind of sensing capabilities of the cold atom clouds to measure signals from astrophysical sources, which I think is such an exciting new application of those same cold atom techniques that are used to study the behavior of quantum materials. So it's amazing how much those experiments have in common despite such different goals. And there are a few other experiments across the world trying to do similar things as well.
I have to say the idea of using interferometry to measure properties of dark matter or gravitational waves, that's kind of mind-blowing to me. And I work in many-body physics. I work in the theoretical side, so I'm familiar with these quantum simulation ideas. I can remember seeing, in fact, one of the first papers from the Aeon Collaboration talking about ultra-cold atoms and using them for gravitational waves, and I could not believe it. I remember reading that paper and then talking about it to everybody I met for the rest of that day, saying, did you know that this was possible? This is incredible.
It's so exciting. I certainly, 10 years ago when I first kind of joined the field, I think the papers that I was reading and the ideas I was being exposed to were certainly more along the lines of this kind of the quantum simulation type applications. And it really does feel that it's in the last few years that all of these other incredibly exciting avenues are opening up.
So is this because of developments in the technology, developments in our understanding of quantum mechanics, or is it just people now have better imagination than people 10 years ago?
So I think a lot of these ideas have actually been circulating for a while. And I think some combination of having the technology there to actually put these ideas into practice, and also some of the original key players continually pushing them and actually pushing for the funding to get the proof of principle. I think that's probably where a lot of this expansion has been able to come from. And then I suppose once you can get some initial investment, some initial studies, then you can get the more people working on it, more creativity, and just better and better ideas as well.
I guess that's the standing on the shoulders of giants idea, isn't it? One
Exactly.
idea builds on another, builds on another.
Yes. I think that's been one very interesting thing about working in the Aeon collaboration has been how many different researchers are involved. So we're very used to, in atomic physics in general, working with one research group, 5 or 6 people working on an experiment. Of course, we talk to other people, certainly want to talk to theorists and talk to other experimentalists about the ideas, but the research itself is much more based within one research group. So it's been very interesting working in a collaboration very closely with not only other cold atom experimentalists, but also high energy physicists, experts on timing and synchronization for large detectors, theorists working on dark matter. I think that has been a big struggle for me, is realizing that I will never be able to understand in detail every single aspect of this project. But that's exciting as well, and it's always so interesting being able to hear from all of these different experts in lots of different areas and realize that we're all working on building something together.
So overall, then, it's quite beneficial in your experience to have these interactions with people from very, very different fields who you wouldn't ordinarily talk to, but who, because of this collaboration, you're getting to learn from.
Absolutely. I think not only in terms of just learning more about the physics and learning how we can better design our experiments to fit a certain detection goal, likewise feeding back to the theorists what the current capabilities of our experiments are, but also learning more about how to work well with scientists from other fields. I think that has been very interesting. I think we're doing it quite well. Yeah, I think we've been quite successful at being collaborative, but also thinking about then scaling up to the size of a lot of the high energy collaborations. I think we've got still a lot to learn about how they work, and really just try and make the collaboration as productive and inclusive and truly collaborative as possible to get the best possible science out, as well as having a happy and motivated team where people feel that their input is valued.
Do you think that this is the future for big sort of scientific experiments, is to have these kind of big interdisciplinary groups, or do you think there will always be a place for these much smaller, more focused groups that you spoke about originally?
I think I think there should be a place for all of those different styles. I think each of those can bring something different. I think maybe the time of the lone genius, if that ever truly existed, um, has probably passed, because, well, firstly, we have, I think, a lot more recognition now of all the different skills that are necessary to move science forward, but also because certainly in experiments, things are scaling up. You cannot be an expert in everything. I think there is still definitely space for those more focused groups who really do want to develop an expertise in something very specific, because there's a huge value in that. But certainly for starting to apply, let's say, cold atom technologies, it's really all I feel comfortable making making that kind of judgment on. But starting to apply those technologies to new fields, new detection goals, I think we do need to recognize other people's expertise and learn how to make the most of that. I think it just makes things a lot more exciting as well. And I'm quite jealous of the students who are just coming up now through the collaboration, because they are truly seeing this very interdisciplinary way of working. They're getting exposure to all of those different ideas quite early on. And I hope that means that if later on a student wants to make a career shift from, let's say, cold atom physics into high energy physics, that they'll have the tools to do so.
I guess working in such a big interdisciplinary collaboration, that must require some very good communication skills as well, to talk across disciplines. Is that something that you found challenging, or did that come naturally to you?
Um, so I guess first I should credit the formation of those kind of communication channels to our amazing project management team. Like, we certainly could not be doing this without them, and without the amazing management and communication skills that they're bringing to the table. So in terms of communication itself, I think that I like to think that I find communication fairly easy. Not necessarily easy, but fairly natural. But it's certainly something that everyone can always improve. And certainly I've learned a lot about, for instance, communicating ideas about, say, building an apparatus to physicists versus engineers, and the very different kind of language and specifications that are necessary for the two different groups. Likewise, I think being able to communicate the kind of more fundamental ideas about your field, so that the other researchers from the different fields can understand, and we can all have this kind of shared platform of knowledge that we can then build on. That has been extremely important. So I'm quite glad that I did kind of earlier on during my PhD practice that really. I always enjoyed doing communication of my research to the public, speaking to school children as well. And I think all of that has definitely helped being able to break down some of the more complicated ideas about my work.
So then you've mentioned a bit about your science communication experience there, and it's interesting that your experience of doing science communication with the public and with public engagement has fed back into your research then. So this practice at breaking down these ideas and explaining them in a reasonably simple way, or reasonably clear way, let's say, that's something that you find beneficial in your own work and part of this collaboration.
Definitely, yes. I think there have been a few kind of tangible benefits actually of that kind of public engagement work. So the first has just been very direct, is that I always feel so enthusiastic about coming back to the lab and doing science after being able to go and talk to a group of people about how exciting the work is. I think it's a really nice chance to stop and take a step back away from the day-to-day kind of some of our work is tedious. We can never get away from that. But yeah, to be able to take a step back from that, see how exciting it is, see how exciting our goals are, always makes me so enthusiastic to come back. But then, yeah, certainly in terms of building communication skills, recognizing kind of how to pull out the important information, not just necessarily the information that you find the most interesting or the details that you've spent the longest working on, has certainly been useful feeding back into the collaboration.
So can you tell us a bit more about the science communication work that you've done in the past then? What kind of things were you involved with during your PhD and in previous years of postdocs?
Yeah, so I feel very lucky that I've worked in universities that have really cared about public engagement. So during my PhD, I did quite a lot of kind of demonstration lectures or tutorial sessions with high school students, so generally between 14 and 18 students who are already interested in physics or interested in science and looking at universities. So there you're always careful. You don't want to try and force physics on someone, but of course you want to show them how exciting it can be. And I think it can be useful to see both the style of work that or the style of lectures that they will see in an undergraduate or a university setting, but then also some of the research applications of that. So how those ideas that they'll be learning about will feed into research later on. So I think most of my work during my PhD was with that sort of age group. And then when I moved to Cambridge for my postdoc, I was really, really fortunate that I could be involved in colleges. So you mentioned that I'm currently affiliated with King's College. Previously, I was also an affiliate of Jesus College. And the colleges do some amazing work, kind of really actively trying to reach out to groups of students to get them to visit Cambridge, get them to experience university life. And that also gave, selfishly, me the chance to try out some more experimental things with my kind of public engagement work. So one thing that I became slightly famous for was teaching a dance routine to try and explain laser coherence. That was always fun. You have some groups of teenagers who are super enthusiastic about this, and then some who are much more difficult to convince.
Is there video of this that we can link on the website? I'd love to see that.
That's a good question. Actually, I'm not convinced there is. I'll take a look and see. But then, yeah, kind of as I got more experience, got a bit more confidence, I had the chance to start to organise some of my own events. And so we have the Cambridge Festival here every year, where you just get loads of researchers putting on engagement events, external speakers coming in. And so I was lucky enough to be able to run some events for for that. So we had one that was delayed or postponed 3 times for COVID. Um, that was a board game that I designed along with some students in my research group, exploring 4-dimensional space and quasi-crystalline structures.
Wow.
So that was great fun to develop. We were so disappointed every single time it was cancelled, and then finally this April we were able to actually try this out with the public, and that was just so much fun, being able to think about, yeah, how can we take this really complicated idea of a quasi-crystal structure and kind of its mathematical representation of 4-dimensional space, and then break it down to, okay, how can you move on this space, and then how can we gamify this? So that's something that I definitely want to try and take a bit further, see if we can get some funding to roll that out, and certainly run the event again, because that was really good fun. And then also more recently, I've started working with primary school children as well, which has been really amazing. So I was inspired by the work of a group at mostly based at Imperial College London. So it's led by an artist called Geraldine Cox. She's absolutely incredible, comes up with some really fantastic creative activities for primary school children, mostly years 3 and 4, to get them interested in different kinds of science. So I joined one of their atom days, where they got the children exploring atomic structure, again, just pre-COVID. And then after that, started developing some of my own workshops, and were able to run some online during all of the pandemic closures. And again, this year we've finally managed to start rolling that out again. So I've got some funding from the Cambridge University Public Engagement Starter Fund to take those workshops back into schools. We're hoping to run an event for families here in the physics department as well at some point soon. So that has been great fun. I am absolutely astounded by how curious and quick small children are. You know, just they have so many questions and they just absorb so much information. So my main goal with some of these workshops is to have, at the end of the session, the children have, you know, had fun doing some creative activities, but they can also come away being able to read and interpret the periodic table and tell you how many electrons an atom has, how many neutrons an atom has. And I've been absolutely blown away. I think we underestimate children a lot. So my goal with that has really been to kind of introduce them to those ideas quite early, you know, well before they're introduced to, say, the periodic table in secondary school, so that hopefully when they get to that stage in secondary school and they're learning it in a much more formal way, that those ideas still seem quite familiar and that they still associate it with having fun. So yeah, that's been really great fun. And certainly if any schools are interested in partnering, at the moment we can work with schools in the Cambridgeshire area, but yeah, if anyone wants to get in touch, then I'd be more than happy to discuss what we can do together.
So is this something that will always have to take place in person, or would you be interested in doing more online workshops and more work with schools further afield as well in the future?
I would definitely be interested in running more online workshops, or discussing with schools how they can run their own workshops. So yeah, I'd be very happy to do that. I think we managed that quite successfully with several events over the pandemic. I love the in-person events, and I think it's really great being able to be there and answer the children's questions directly. But at the moment, the funding that I have will let me travel in the Cambridgeshire area. I'd certainly like to look into being able to travel further afield. So that's a plan for the future. But yeah, at the moment, well, Certainly, if anyone's interested, they get in touch and we can see what we can do. Or, of course, there are networks of people doing really amazing outreach work as well, all across the country, all across the world. So even if it's a matter of helping people find workshops that are being run at universities in their area as well.
It's really interesting, actually, to hear you talk about public engagement, because the first question I ask every guest is what got them interested in quantum physics or in physics in general. And it's surprising, some guests say they did get interested at a very young age when they first learned about things like atoms. And I don't know, I wonder now, maybe in 15 or 20 years, someone will be doing a podcast with a with a leading scientist, and they'll say, well, Dr. Tiffany Harte gave us a workshop when we were in primary school, and that's what inspired me.
That would be amazing. That would make my life worthwhile.
But it is great to hear that that public engagement and science communication is so important to you, because I guess we all got into science because at some point someone inspired us to do that, or I don't know, just made us realize that this was an option to us. And the more people
Yes.
we can reach with that method, the better.
Absolutely. Yes. I feel so lucky with all of the teachers and lecturers that I've had over the years. Definitely owe a lot to them.
Well, then I guess looking back over your career then, so you've done your undergraduate, your PhD, and then several years of postdoc, now all in the United Kingdom. And it has to be said that physics historically has been a very male-dominated field, a field dominated mostly by white cisgender men for a very long time. Is this something that over the course of your career you've seen changing in any way? Ideally, hopefully for the better, but of course we still have a long way to go. But have you noticed anything change over the years that you've been working in this field? And are there any initiatives that you're aware of that are changing things for the better in the UK at the moment?
Yeah, so I think that's a really interesting question, and in some ways quite difficult to answer because my career is somewhat limited. So I've been working in cold atoms full time for 10 years now. That followed an absolutely amazing undergraduate experience. I'd say during my undergraduate years, I never really thought about sexism in science. Possibly should have thought more about the broader aspects of diversity. But then as I went into full-time research, that was probably when I just from personal experience, so this is all anecdotal, maybe started to notice that this was something of a problem. So over those 10 years of PhD and then postdoctoral research, I would say in a sense, I feel that my experience is that some of those issues are becoming worse. But I do think that part of that could just be that as I'm increasing in seniority, maybe you're just hitting more of those problems more often, or kind of approaching situations in which there can be more of a challenge. I think maybe my expectations have changed. I think as a PhD student, I didn't expect anyone to respect my expertise, and I almost didn't. It's not that I didn't mind, but I wasn't surprised by being spoken down to or overlooked. Whereas now, I'm not sure whether my tolerance for that has diminished, or I have more of an expectation that, or a realization that I do have, you know, valuable things to bring to the table, which of course is true of PhD students as well. And everyone should absolutely be treated with respect in their professional lives as well as their personal lives. I should say most people that I've worked with, you know, haven't experienced any problems. I think I've been incredibly lucky in comparison to a lot of people. Um, but yes, just purely anecdotally, the trend that I have observed has not been a particularly positive one. Having said that, I think there is a lot more discussion now, a lot more open discussion about issues relating to diversity and inclusion in science, and that is definitely a positive. I remember during my PhD time, it was very much the kind of lean in era, where I kind of felt that you're being told, kind of often implicitly, but if you're having problems, it's your fault. You're not leaning in enough, or you're not presenting yourself in the right way. And I think there is an increasing expectation from the broader community now that actually no, it's our culture that has to improve. So in that regard, in the broader cultural conversations that are happening in the research community, I think that is very positive. I'd say in general as well, there are a lot of individuals who are doing incredible work towards equity, diversity, and inclusion, but that it seems as though those individuals are often really burning themselves out, working incredibly hard against a system that isn't changing as fast as it should. So I do think that a lot more institutional and cultural change is needed across, well, probably, to be honest, all of society, but definitely across research. The question of how that cultural change will work, I wish I had a nicely formed answer for. I hope that it will be enough that as time goes on, as these conversations keep happening, that will happen naturally. But I suspect that, more kind of institutional level changes will have to be made.
So it sounds like the burden of fixing this problem is being placed very heavily on the people who are most disadvantaged by the problem already, just compounding the issues then.
That's certainly how it seems. And if you look at the working groups on equity and inclusion, very often they are made up of already underrepresented groups who are facing struggles associated with kind of the institutional problems, and then also, like you say, facing the burden of trying to fix them. Again, there are individuals everywhere who are doing incredible work, but yes, I think maybe that's it. Maybe it's more people need to be involved in those conversations. People who feel like those issues don't affect them maybe need to take a bit more responsibility for learning and getting involved, while obviously making sure that we're always listening to the people who are affected.
Okay. One final question to end with then. If you could go back in time and give yourself just one piece of advice, what would it be?
Ooh. Sticking to just one would be difficult. I think I would tell myself to be more confident about trying new things, just trying things out, seeing how they work, seeing how you can learn, and not being afraid to make mistakes.
Okay, I think that sounds like a pretty inspiring lesson to end on. So I think we'll wrap it up there. If our audience wants to learn a little bit more about you and the work that you're involved with, where can they find out more about you?
So I am on Twitter at ultracoldtiff, and also my department website.
Okay, perfect. We'll make sure to leave a link to your Twitter profile and your website along with the transcript for this podcast on our own website. Okay, thank you very much, Dr. Tiffany Harte, for your time here today.
Thank you very much.
Thank you also to the Unitary Fund for supporting this podcast. If you've enjoyed today's episode, please consider liking, sharing, and subscribing wherever you like to listen to your podcasts. It really helps us to get our guest stories out to as wide an audience as possible. I hope you'll join us again for our next episode, and until then, this has been Inside Quantum. I've been Dr. Stephen Thompson, and thank you very much for listening. Goodbye.